In this video, we'll be discussing exponential growth and decay. The exponential growth and decay formula is denoted by some function is going to be equal to the initial amount of population times e raised to some constant times t. Again, the y of 0 is the initial amount of population, t is time, and k is represented by some constant called either the relative growth rate or the rate of decay. Now, if k is a negative number, then you're going to have a decay. You're going to have some amount that is going to decay exponentially over time. If k is greater than 0, then it is going to be an exponential growth. So for example, So finding the unknown variables, the world population was 2,560 million, or I guess 2 million, The world population was 2560 in millions in 1950 and then 3040 in millions in 1960. So first find the relative growth rate. So again, we know that the formula is the initial amount times e raised to the kt. Well, we know that at 1950 it is 2560, and then at 1960 it is 3040. So if we represent this being time 0, then this would be represented 10 years later. So the initial amount was 2560 k times 10 because 10 years have passed and it reaches 3040 10 years later. You would first divide by 2560 and you would get 1.1875. That equals e to the 10k. Now to solve for e, I'm going to need to take the natural log. That helps me to get rid of e. And then I'll divide by 10. So k is the natural log of 1.1875 divided by 10. So k equals 0.017185. So roughly what that means is if you use that in percentage formula, that means the growth rate is roughly about 1.7% would be the relative growth rate of the world population. It is growing 1.7% every year. Now, write the formula for the population. So now that we know k, don't keep it as a percent, make sure it stays a decimal. It says estimate the population 1963. Well, the initial population was 2560, e raised to the k, which we now know, times t, and we want to know when 1963 is going to be 13 years after the initial population. If the initial population was in 1950, then 13 years later, so we're going to plug in 13 in for t, and we will get 3,200.84, but don't forget this is in millions of people. So by 1963 there was a lot of people. Radioactive decay is doing the rate of decay in this case for k. Most rates of decay are in terms of half-life, which is the time required for half of any given quantity to decay. So for example, the half-life of radium-226 is 1590 years. So let's say a sample has a mass of 100 grams. We want to know what is the mass of the sample that remains. So basically we want to know the formula. Half-life means is when half of it has decayed. We know the half-life is 1,590 years. Now let's say the initial amount is 100 grams. We do not know k, but we know that after 1,590 years, then only 50 grams would remain. Why 50? Because it's half of your initial amount. If you started with 100 grams, that means after 1,590 years, you only have 50 grams left. So we're going to use this amount in order to find K. So the first thing we do is divide by 100, and we get 0.5. And now to solve, in order to get rid of the E, we're going to take the natural log of 0.5. And so K is going to be the natural log of 0.5 divided by 1,590. So K is a negative 0.0004,359. That is the rate of decay. Now, because it is a decay, should it be negative? Yes. If you did not get a negative here, then something went wrong, because a negative is representing something decaying, just like in the graphs at the very beginning of this section. When will the mass be reduced to 30 grams? So we're going to take our formula, which is 100 e to the 0.000436 to round t, and we want to know when will this equal 30 grams. So divide by 100, you'll get 0.3 e to the negative 0.000436. And now I'm going to take the natural log, and that will get rid of my e. And we will get time equals 2,761.4 years is how long it will take for this substance in order to be reduced to 30 milligrams. A population of protozoa develops with a constant relative growth rate of 0.79. That represents K, per member per day. On day 0, the population consists of 2 members. That means that is your initial amount. So we'll have 2 times e to the k t. That is our formula, and we want to know what is the population after 6 days. So all we have to do is plug in 6 for the amount, and we will get 234.99. So roughly 235 population of protozoa. Okay, we know that it is the initial amount times e to the kt. Now, we know that the half-life is 28, which means the first thing we have to find is K. We know that after 28 days, only half of it's going to be left. So if you had 50 milligrams, that means after 28 days, there's only going to be 25 milligrams left. So we're going to use these numbers in order to find K. So first divide, and you'll get 0.5. Do you notice a pattern here? 0.5 represents 1/2. A half-life is basically half. So it will always actually give you 0.5 anytime you're going from the initial population to half of it. And now to solve, you need to get rid of e. So I'm going to take the natural log of both sides. So therefore, K represents negative 0.0248. It should be negative because it is decaying. So far, we're good. So the formula is going to be the initial amount, e raised to the kt. And now it wants to know, find the mass remaining after 40 days. So we are going to plug in 40 into this. And you will get 18.54. So therefore, after 40 days, roughly about 18.5 milligrams are present. How long does it take for the sample to decay to a mass of 2 grams? So we now do not know the amount of time. So we have to leave t by its alone. And we are going to set it equal to 2 because we want to know how long will it take to get to 2 milligrams. So first divide by 50, and you will get 0.04. To solve for E, I'm going to take the natural log T will give us 129.79. In this case, this is days. So almost 130 days it will take in order to decay down to 2 milligrams. A sample decayed to 94.5% of its original after 1 year. What is the half-life? So we do not know the initial amount nor the final amount, but we do know the percentage of it. So let's just say that it starts with an initial amount of 100 milligrams or grams. You know that after 1 year, it's down to 94.5 milligrams, because if it's 94.5% of the original, if you start with 100, that means it's down to 94.5. So therefore, you will get 0.945 if you're divided by 100, e to the k, because k times 1 is just k. So the natural log of 0.945 gives you a negative 0.0566 if you were to round. And it should be negative because it is decaying. So that is k. Now we got to figure out the half-life. So we still do not know anything. We know the half-life, sorry. So what we do know is if we start out with 100 milligrams, we want to know when is it going to reach 50 milligrams. Now, you may ask, why in the world am I using 100? How do you know to use 100? Well, if we used 50, then we want to know when does it reach 25 milligrams. If we start out with 300 milligrams as a sample, we want to know when is it going to reach 150 milligrams of the sample. We're wanting to know half of the sample, so it doesn't matter what you start with, for example 100, we want to know when is it going to reach half of that. So when you divide by 100, you will get literally the number 1/2, which we've been discussing is 0.5. And that gives you e to the negative 0.0566t. So to get rid of e, we're going to take the natural log, 1/2, I just do 0.5 to make it easier. When we divide, we will get 12.25, and in this case, it's in years. So therefore, the half-life of this sample is 12.25 years.